Here's a problem that's angled off a cliff. You can see we have the parameters here, 16 meters per second, 28 degrees, angled off a cliff that's 32 meters high. And these are the parameters that I'm looking for. We're going to start by getting Vx, which is V cosine theta, and then Vy, which is V sine theta. Typically that's where you want to start for all of these problems when you're given an initial velocity along the trajectory. You want to find your x and y components. The next thing I went ahead and did right away is I found my time to the top. That was letter B here that I asked for, by using V initial y over g, and I get a time to the top of 7.66 seconds. Then I went ahead and used time to the top to find my y max. Now that y max is from a point of 0, 0, so it's from the top of the cliff. So this 0, 0 is at the top of the cliff. So the y max is just from that level up. Now if I want to get the total height from the ground all the way up to that top, I need to add that y max to the 32 meter high cliff. And I get 34.8 meters from the top back down to the ground. So using that number, the 34.8, I can figure out how long it takes to fall. It's just a free fall problem. If I know that something is 34.8 meters off the ground, then by using this equation, I can find out how long it was falling for. So all I did was just take this equation here and I rearranged it for time. And if you plug in your parameters there, you get 2.66 seconds. And that number is what we call time, instead of time to the top, we call that one time to the bottom. So that's time to the bottom. Now, what you want to do then is you can go ahead and add your time to the top plus the time to the bottom. And when you have that, you get your total time for the flight of that projectile off of that cliff. That's the first way that you can solve for time. There's a more efficient way to do that by using the quadratic formula. So if you want to do it that way, this is how that would be done. You would go ahead and use your big giant y equation here that has both sets of variables there. It's not just the half gt squared. It's the whole equation. Of course, what we're doing is for a, we're plugging in g as a negative 9.8 meters per second squared. And that changes our equation to what you see here. Then you're going to go ahead and plug in your height, which in this case for y is negative 32. It's negative 32 because, again, the top of the cliff is 0, 0. So if that's where 0 is, then if you're looking at a cliff that extends 32 meters below that, that's where the negative comes from. So you have to make sure you plug that in as negative 32. Once you get that plugged into the equation, you set the whole thing equal to 0. Plug it into your quadratic formula. Hopefully you've learned how to do that in your calculator by now. Remember that the negative time would be at some point before that projectile was launched, so that's not the one that we want. And you take the positive time. So as you can see, both ways, we ended up with a time of 3.43 seconds. To find the range, which is the last part of that problem, you just simply plug that into x is Vx times t. You have to make sure you plug in your total time and the x component of your velocity, which of course the x component of your velocity always remains constant. No matter where you're at on the path of that projectile. So that number will be the same at any point along the path. The next problem that we tried that was very much like this was the ski jumping off the ramp. Here's the key for that one. There are some additions to this chart. You want to make sure you put in A, B, C, and D down the side, and that corresponds with these points along the path of the trajectory here, A, B, C, and D. A is at a point of 0, 0. B is at the very top of the path. C is at some random place that is 4.3 seconds into the flight of that ball. And D is back down at the ground. I also want to add in a coordinate plane here. If we put in, oops, didn't mean to do that. If we put in a little axis here, and that's 0, 0, everything to the top is going to be positive, and everything below this point is going to be negative. Likewise, everything to the right of your y-coordinate is going to be positive, and everything to the left of your y-coordinate is going to be negative. And the point we're starting at is 0, 0, right at A. So again, if we're looking at the height of the cliff, this height down here, this height of the cliff, is going to be a negative height, just as a reminder for that. So the answers are here. If we take a look at the next slide, you can see there's some worked problems here. Vx and Vy have been solved for you. Also, to find out the total time in the air, went ahead and used the big Y equation and the quadratic formula. And just to clear up, the negative times we're not going to use. We also found T to the top, and that here, this T to the top, is to get from point A to point B. So that's how long it takes to get up to B, is 1.8 seconds. Which means that your Y max, if you use that number, it's going to be just from your 0, 0 up to point B. We can find the range. If you plug in any time along the path, you can get your range. So your range at 1.8 seconds is 59 meters. Your range at 4.3 seconds is 142 meters. Same with your velocity. Using this equation here, if you plug in your time, you can get your velocity at that point. So your velocity at 4.3 seconds is minus 24.7. Your velocity at 5.7 seconds is minus 38.5. Again, it's negative because it is below, it's down here. It's below our 0, 0. On the next slide, here's the example of that football problem where we've given a certain set of parameters here, being out at 25 meters and 3 meters off the ground. I'm asking, does the football make it through the goalposts? Several different ways that you can solve this problem as well, but I think the easiest way is to do it the way we've been doing it, using the big Y equation here, and saying how long does it take the ball to go 25 meters, and it takes the ball 1.82 seconds to go 25 meters. So we plug in that 1.82 seconds into the Y equation, and you can get how high off the ground that ball is at that time. So again, this equation will tell you the height at any given time for anything that's flying through the air. And the reverse is true. It will give you the time if you know the height at any given place. So what you could do is you could plug in 3 meters for your height here, and because that's the height of the goalposts, and then solve for time that way. If I had asked you, how long would it be in the air? On the next slide, we changed the parameters of that and said, well, what if there was a bad snap? we're playing Lake Forest in football, and they had a bad snap, and it changed the parameters just slightly so that now we have 16.5 meters per second and 46 degrees. Does the ball now get kicked through the goalposts or not? So we went ahead and found our new Vx and new Vy and solved for the new height, and you can see indeed it does not go through the goalposts because it is not more than 3 meters off the ground. So yay Mustangs. That's all for this slide.